Okay, continuing along, folks. So we're going to talk about the fates of our electronically excited states. I know that you've also spent time talking about this in some of your other classes, so we'll just try to touch on the unique Chem type stuff. So here are some definitions, and again, I expect that you have likely had some of these definitions before, but all the same, let's review them. So stimulated absorption, transition from a low energy state to a high energy state, and the absorption is proportional to the intensity of the stimulation. So we've discussed that as having strong overlap or having a strong transition dipole moment. Stimulated emission is transition from a high energy state to a low energy state. And the emission is proportional to the absorption. Spontaneous emission is transition from a high energy state to a low energy state at a different frequency than the absorption. So it might seem like stimulated emission and spontaneous emission are the same, but they are different. Stimulated emission is occurring at the same frequency. Spontaneous emission is occurring at a different frequency. So intersystems crossing is a non-radiative transition between states of different multiplicity. And what helps me remember that that's non-radiative is this crossing. So like it's crossing over from one state to another in a non-radiative way. Internal conversion is very similar to internal intersystems crossing. So it's non-radiative. However, the multiplicity is conserved. So again, we have two other twins here. Intersystems crossing, non-radiative between different multiplicities, and internal conversion, non-radiative of the same multiplicity. And so then, hopefully you've heard of these before, fluorescence and phosphorescence. Fluorescence is stimulated absorption followed by spontaneous emission always at a lower frequency than absorbing. And in fluorescence, multiplicity is conserved. And because multiplicity is conserved, the lifetime of fluorescence is very fast. In phosphorescence, this is very similar to fluorescence, stimulated absorption followed by spontaneous emission at a lower frequency. However, multiplicity is not conserved, and thus the lifetime of this process is very slow due to it being spin forbidden. So let's look at some of these things on a diagram here. So the first one we'll stick to is fluorescence. And so again, noting that our stimulated absorption will go via the Franck-Condon process. So we'll go from a ground vibrational state of the ground electronic state that is most closely resembled by a vibrational state in the upper level that has strong overlap. And now in our fluorescence, we will see a very similar thing as what we saw in absorption. However, the emission is related to a strong overlap in the upper state to a strong overlap in the lower state. Okay? So as you might imagine, we could also get fluorescent lines occurring from these different vibrational levels, but those would occur at lower intensities depending on the overlap. If the overlap is not as strong, the intensity won't be as strong. So now in phosphorescence, we can see a very similar thing. We've got stimulated absorption to an upper lying state that most closely matches that of the lower lying state. However, in this case, we're transitioning in our multiplicity. So notice our absorption is going from singlet to singlet, which would be allowed. However, because phosphorescence involves a change in multiplicity, presumably there would be an intersystems crossing observed where we have a triplet state that very closely matches the energy of a singlet state. So this is really the only time we would observe intersystems crossing is if we have a vibronic energy level that is very close or even nearly identical to that of the other multiplicity. So now intersystems crossing occurs from the singlet to the triplet, and then now the triplet can undergo phosphorescence back down to the singlet, and again, in a similar process where there's a wave function in the upper state that most closely matches the wave function in the lower state. And if we could look at the time of this, we would see fluorescence occurs very quickly. So both of these are occurring as first order decays. So that means these are exponential. So that will be e to the negative kt will be the rate of this process, where k is the first order rate constant, or we note the lifetime of this process will be 1 over k. So when we talk about the lifetimes of these processes being very long or very short, we're talking about the inverse relationship of their first order rate constant. Continuing along with this notion of absorbance and fluorescence, so a UV-Vis absorption spectra closely resembles the vibrational energy levels of the upper lying state. So I'm going to make a note of that. Absorption gives us the upper vibrational levels. So this is like a brief note, upper vibrational levels. So in other words, the spectrum of absorption, we're going to see the upper vibronic levels. A fluorescence spectrum, on the other hand, fluorescence, as you might imagine, represents the lower vibrational levels. Okay, my handwriting has really gone to crap here at the end of the semester. Apologies. So the fluorescence spectra, because now we're looking for overlap from the top down, our fluorescence spectra will really show us the vibronic ground levels. So for example, if we look at these spectra here, and these are our vibrational levels given as nu final and nu initial. So we can see 0, 0 right here. Those will overlap with each other. They will occur at the same energy, because now if we think about that, 0, 0 would correspond to going from this state down to this state. I'm not sure why that did that crazy thing. So the spectra of absorbance and the spectra of emission will match, right? Because if I go from 0 to 0 in my absorption, it's the same energy level as my emission. However, because now the overlap of these states will be different, we'll see different intensities, right? And so that's why in the case of this fluorescence spectra, the intensity is maybe somewhat lower than the absorbance intensity because of the mismatch of the overlap. And then now, as we go to smaller wavelengths or higher energies in the absorption spectra, we're going to see overlap with these upper lying states. So here, that lambda max might occur to this blue line given here. However, here, the lambda max in fluorescence will represent the best overlap going back down. And so if we have molecules with interesting vibronic structure or well-resolved vibrational levels, we'll see these interesting features. If we don't have well-resolved vibrational levels, or we're doing this continuum absorption, then our absorbance and fluorescence spectra will just look very similar to each other, albeit featureless. And of course, the fluorescence will occur at longer wavelengths than the absorbance. Okay, so I know that you all have gotten some experience doing Jablonski diagrams in 441, and we will get into those types of diagrams during our live lecture. I will see you then.